So thanks for coming again. So let's review what we have discussed for the previous two lectures. Still a little bit. Maybe it's not close enough. Does it work better? So the main reason I introduced the homology language in a fair detail was to make you comfortable with the notion of generalized toric codes in various dimensions. And there's one correction I want to make. I said this funny notation that like a 1,2 or 1,1 toric codes is, well, the number is not too well motivated, but there is a good motivation for that. The logical operators in such a model is given by this homology groups, and the dimension of that homology group is directly related to the shape of that logical operator. In the 1,1 toric code, the usual two-dimensional toric code, you have a H1, and that 1 represents the fact that you have a string operator, which is one-dimensional. If you go to 3 dimensions, there is a 1,2 and 2,1, and there was an exercise that to show 1,2 is equal to 2,1. And there 1 corresponds to one type of logical operator of dimension 1, but of X type. But in the other case, you can the second component represents the the second homology group given by this second number is related to the shape of the sigma z type logical operator. The pattern is obvious. If you have a certain dimensional logical operator, the conjugate operator that acts on the logical qubit lives on the conjugate dimension. And the important thing here is that, well, k plus n minus k was equal to n. So there is some dimensional duality between the logical operator's shape. And then we discussed about the question of quantum memory, and I briefly sketched how the problem is generally set. You should design or you should define what your memory is, and that amounts to, in the information language, to define the encoding scheme. And for a condensed matter theorist, that amounts to defining your Hamiltonian or some other dynamical system. And then we analyze some type of noise, and that is dynamics. And then you should conclude your study of quantum memory by devising a quantum classical algorithm to prepare your state to be ready for your next information processing step. That amounts to decoding algorithm. This is somewhat condensed matter doesn't really care about, but in a sense it does. Let me give you a trivial example. We discussed about the Poirot's arguments applied to the two-dimensional Ising model. How do you define, well, when you encode a bit information into that ferromagnetic, how do you read that encoded information? If you just look at the single spin, then there's a non-trivial chance that you're going to be fail. I mean, single spin can be flipped at any time by some thermal noise or any other noise. The probability will be flipped is small but non-zero. What you have to do is you look at the large number of spins and average. And that averaging sounds natural, but it's kind of the decoding algorithm. We know that it works well because of the number of large the law of large numbers. with the assistance from the energy barrier provided by the Hamiltonian. So even in the classical regime, there is some decoding algorithm. You write, well, if you study the ferromagnetism, you write down the expectation value for the polarization. Why do you take expectation value? The naive value doesn't make any sense. You have to ensemble average or expectation value with respect to the quantum state. That makes this quantity robust. And taking the average amounts to the decoding algorithm. So for the quantum memory problem, you should always think of these three components simultaneously. And that's one of the features that makes the problem interesting. And then I concluded with the worrisome remark that in the toric code, the bulk is a corrective region. The erasure of the almost all bulk does not harm your information at all. Therefore, by looking at the equivalent conditions for the error correction, we concluded that there exists an operator that resides on the complement of that majority bulk. But the complement was happened to be the union of two strings, and the dynamics would resemble the one-dimensional case. So if you're really concerned about the fundamental limit of quantum memory using the toric code subject to thermal interaction, then it is not very good. The topological order system is believed to be, well, it is advertised to be good for quantum information processing. However, it only under the assumption that your temperature is extremely low. There's no scaling with respect to the system size. And we want to do better than that. And there's an obvious solution. In the 2,2 toric code that lives on the 4 dimensions, 4 plus 1 dimensions, your logical operator corresponds to the second homology of your manifold. And being surface-like implies that your dynamics will be much similar to the 2-dimensional Ising model in the classical regime. So it's a perfect solution from this quantum memory question. We have a definite encoding scheme because this code, the ground space, forms a error correcting code. So we just embed our qubit into that. And noise will not do two bad things for us because the dynamics will be very similar to the Ising model, for which we know there's a critical temperature below which the magnetization is surviving. The same logic goes on here. Your thermal error will not flip your logical qubits. Decoding algorithm becomes non-trivial because we cannot simply take that average. It's a quantum information. You should not measure individual qubits. Now, what's the decoding here? All we have to do is just get back to the original encoded code space. So if my 4-dimensional system is this box, then there should be some domain strings. Inside, errors have occurred, and the Hamiltonian puts energy penalty across this string boundary. Along that string, whose energy grows. If we imagine that we cool it down, then you can see that these string will have, since this string have a string tension, and lowering temperature means that you're reducing the entropy contribution. So it will shrink down, and as you approach the 0 temperature, the string will be just point and disappear. And by the statistical argument, probability that you don't shrink any large group is high. In other words, you almost always succeed to remove all errors in your system. And that is my decoding algorithm. You may think that, lowering the temperature is somehow a non-physical thing to do. Then you can do it on the algorithm level. Just measure the locations of this string. That measurement would not harm your quantum information at all. And then in your simulation, identify how should I shrink them. And the shrink them amounts to apply certain operator inside. So right before you read it, your quantum system for further processing, you just apply the operator and use it. So in that sense, the quantum memory problem using this 4-dimensional system is solved. Now, you see the gap. We discussed the 2 dimensions, 4 dimensions. What about 3? So before I go to the 3-dimensional example, let me give you an one exercise. I think of a hexagonal lattice with qubits or spin halves per every vertex. And then I consider the Hamiltonian a 12-body interaction Hamiltonian, again a stabilizer code, and one term looks like yeah, there's a one vertex here. Did I draw everything? No. Yeah. So it's a product of 12 polyspins. And the same pattern goes for the sigma x part too. Any question about the definition of the model? Okay. Now the exercise is that examine the elementary excitations in this model, and then show that so hexagonal lattice, qubits per site in that hexagonal lattice, and I place sigma z across all the corners of hexagon and their legs.
And their what?
Leg. So yeah, you see the leg. So maybe I could call it as an insect model because this has 6 legs. For a proper credit, this model was asked to me by Sagar BJ some years ago. I forgot which year exactly. And his question was whether this model can be a fracton. The answer is no. And how to show that it is no is up to you.
Sigma x is also on the same?
Yeah, exactly the same pattern. And, well, the second question is more challenging. You should map it to the 8 copies of the toric code. Yeah. So why am I giving you this exercise? So this is to illustrate the some non-triviality when the geometry is slightly changed, and the fact that there's some fundamental limit in the 2 dimensions. Yesterday we briefly discussed, well, maybe that board is better. Whatever topologically ordered medium you may design, in order for that medium to be stable against arbitrary perturbation, it better be a quantum Everything correcting code. And typically, your model will be translation invariant. So small region will be largely the same as any patch that doesn't involve boundary. So likely, your entire region, except for that small strip, will be correctable against the erasure channel, erasure error. In other words, even if you forgot everything here, you should be able to access the ground space by acting on this strip. Now, why the strip is important? Strip looks like a one-dimensional, quasi-one-dimensional system. So if you have some operator that acts on the ground space, if I just truncate it here, and then only I apply that portion of that operator, then there should be some excitation at the end. And from then on, you can resort to the intuitive dynamics of one-dimensional Ising model, where these defects will be mobile across that string. So this argument, well, is not a mathematical proof, but this suggests that according to this purpose, this two-dimensional model will behave pretty badly. And that example is a non-trivial test of this argument. It's a local Hamiltonian, but you will realize that excitation here and there actually belongs to a different topological sector. Nevertheless, single excitation, for single excitation, say here, you should be finding another single excitation somewhere else, but of some finite distance, such that two of them fuse to the vacuum. So yeah, this is not non-trivial check for this claim. So coming back to the three-dimensional question, we have to ask a more fundamental question. What prevented us to construct the stable quantum memory against thermal errors? Well, comparing the three-dimensional or 1,2 or 2,2 toric codes, the essential bottleneck was the existence of a string-like operator, which was unavoidable by that suggestive argument in 2 dimensions. Can we get rid of them? That's the motivating question. And this question is wonderful in the sense that it's a yes or no question, and either answer gives us something useful and perhaps meaningful. If yes, there exists a model without any string-like operator, then itself is great. It's ideal. Well, in this idealized quantum computing engineering effort, that's great. And it is great in terms of condensed matter too, because so far any topological order system design resorted in some homology type elements in it. And whenever you have such a topological element, the dimensional duality appears to be unavoidable. Then you end up with the string operator again. So you are breaking the paradigm there, if the answer is yes. If the answer is no, that every model in 3 dimensions must have a string operator, that alone is an interesting consequence. The error correcting criteria, if you carefully look at it, there's no element that depends on the ambient space dimension. You know, the error correcting criteria was existence of recovery map, decoupling with respect to the some entangling environment, or the ability to act on the ground space by acting on some complementary region that you want to forget. So none of them has a very special resort to the dimension, but somehow, if my original question had answered no, then somehow implies and specializes in 3 dimensions gives us deep result. So in that sense, that's an excellent question. But now let's think about the question more carefully. What's the string in the first place? If you're writing down a field theory on the continuum space time, then a string, that's out of question. Why do you ask that? It's a continuous map from some interval or circle into that space. That's it. But when it comes to lattice, what does it mean to have a continuous map? Well, strictly speaking, any continuous map in the lattice is just a point. It's a discrete, and your interval, the domain of your curve, is a connected region. So any continuous map should map entire interval to a point. The point is a line, of course, but point has a point. So in the lattice, what is a string is another non-trivial problem. And here's an illustration why that question is non-trivial. Point is a point. 2 point is a 2 points, a finite set. Many points looks like string, but it's a collection of points. Three rows of dots looks like string, but it's somewhere between plain and a string. Where's the boundary? At which point should I call it as a string, and at which point should I call it a surface? What's the boundary?
But doesn't the Hamiltonian in some sense gives you some notion of locality and some geometry?
Well, my most general Hamiltonian will act on this square. Square almost looks like a point. Collection of squares, well, that's collection of squares. So, yeah, there's a, yes. Good question. Actually, that's the one of the main intuition I wanted to convey throughout this lecture, but the rough answer is that you started with some topological manifold, and you designed the particular triangulation or cellulation that respects underlying topological manifold, and you design your Hamiltonian in such a way that it directly absorbs topological data and nothing else. Said differently, your Hamiltonian design was more than just lattice model. It was a scheme to define a Hamiltonian on every lattice derived from triangulation. It's more than a lattice model. It's a collection of a procedure, or Zhenghan Wang told me the word schema. I'm not sure if that's a mathematical term, but it's more than just a single Hamiltonian. But now I'm asking the reverse question. Given a single Hamiltonian, how can I say about the strings and surfaces and dimension in general? So generally, I don't think there is a way. So what I resort to is my original question: to have a non-trivial energy barrier. So, here's my resolution. A string is a collection of operators my English was my primary language, so such that it creates So I think of a set of operators that obeys these two rules. So implicitly, I'm imagining some Hamiltonian, and I wish to define what the string operators are like. And here's my criteria. First one is that strings have two endpoints, which is natural. So if you apply that string operator into your ground state, then it should create excitation at two locations, which would be the endpoint of my string. But I did not say anything about the say explicit geometry here. And the second criterion is that the distance between the two in that collection, two excitations, two boxes that encloses the excitation can be arbitrarily large compared to the width of phi, the width of the support of phi operator. So in this way, I have, well, the only ingredient I used is the notion of metric, notion of distance. There's no topology going on. There's no continuum, or it doesn't care about the continuum or a lattice. Just the abstraction of the fact that string has two endpoints. Yeah.
box that contains the excitation.
Yeah. The box encloses the excitations.
Would this be different than if you embedded your lattice into manifold in some metric preserving way or nearly as possible, and then consider the manifold definition of curve but fattened by some finite amount?
It may affect it by that, yes. Well, as long as your mapping is isometry, it doesn't matter.
Yeah.
But otherwise, it will be affected. But I'm thinking of a single metric space. So, yeah.
But that's an equivalent definition of string operator to what you just gave.
Oh, you're considering the condition to be phrased as it should remain string-like under any iso.
Yeah, basically the width should be finite.
Yeah. That's another way of phrasing, yes. Well, then, yeah, that's equivalent. So the fundamental question I posed earlier, as you may have known, has answered yes. That there exists the Hamiltonian model that lacks any string logical operator. And let me draw that one example. It's a one example, not a unique example. By no means it is unique. I hope to convince you that there's a zoology or typical, in some suitable sense, model will have no strings in that sense.
Can you say,
Yeah.
can this question, whether it exists or not, it's posed in terms of homology, in terms of H2, or in terms of H1?
No, I wish to avoid that. So it's not an argument, but just the imagination that if I started with the Hamiltonian construction that has elements from the topological homology groups, then I think I would inevitably get a three-dimensional model with strings because of the dimensional duality. Yeah. Yeah.
So we want to avoid the logical operators which are one-dimensional, right?
Yeah.
But why? Why do we look for codes that don't have them at all? Why can't we just go for three-dimensional Turing code and just use another? So we have this C0, C1, C2, C3, and we can use not one-dimensional or two-dimensional.
Great question. So maybe that was the point I glossed over. So indeed, well, H1 arises because I constructed a model using this portion of this chain complex. What if I consider that part? That's your question. Yeah. Well, if you construct a model starting with the green box here, then you would derive 2, something model, but you will later realize that something turns out to be 1 again.
Okay, so reciprocal.
Yeah. So 3 is funny. So 3 is a 2 plus 2. 3 is 1 plus 2, and 1 must be there.
Okay.
Yeah.
So would that just amount to changing the x's by z's and z's by x's?
That's the solution of the exercise I gave you. That the equivalence between 1, 2 and 2, 1. Yeah. Okay, so so the plan is that I give you an example, realize it is complicated, so that will motivate you to introduce some other technique, and then explain that technique for some time, and then return to the model again. Yeah, I'm trying to draw the simple cubic lattice in 3 dimensions, but I can only go to depth 1. And the rule is that I'm going to define Hamiltonian terms only for the black cubes of my checkerboard. Okay, so in 2 dimensions, the checkerboard pattern is just this, and in the 3 dimensions, you blow up by this unit interval, and the next layer is the inversion of this pattern. So more clearly stated, I color the cubes of whose coordinates sum to even number. Okay. So I'm trying to draw that checkerboard pattern here, but I'm limited to depth 1 here. So please understand that. And the qubits live on the vertices. And yeah, every vertex. And the model is I omit the very the inside one, but I insert another z at coordinate 2, 2, 2. So this origin is 1, 0, 0, 0, and I filled up all the vertices except that origin, but included a vertex at 2, 2, 2. Okay, it's a product of 8 sigma z's. So if I were to draw that, then I should draw somewhere here. Okay, any question about that diagram?
Will then be involved in the next cube as well.
Yeah, yeah. So it will touch the other cube.
Is he only on the black or the white square?
So Hamiltonian terms are associated with each black cubes, and this is one of the black cube. And there I define the model like this. And the sigma x term, well, again, I have to draw the other thing, but it's a direct lattice inversion of this.
Maybe the x's do the same thing for the open, for the white.
No. Both z and x live on the black cube, but the x is defined by the same diagram, but lattice inversion of it.
Oh.
It's sticking out that way.
Yeah, so there was a diagonal sticking this way, but the x in this case going that way. Okay?
So you would skip 1, 1 or something, 1, 1, 1.
Yeah. Right. So in the x case, I would fill every vertex but 1, 1, 1, and there will be another. So there are 7 of them, and the 8th one is at -1, -1, -1. Okay. And the grand claim is that this model is a perfect error correcting code in the usual sense. The bulk erasure can be corrected. Nevertheless, any operator you draw as a string will be equivalent to a local operator localized at the boxes that enclose the excitations.
Sorry, can you repeat the last thing?
Any operator that is a string will be equivalent to disjoint operators acting at the 2 boxes that included that enclosed excitations. So probably you have not seen this model before. and that's intentional. This is a variant of the model you have heard about before. But the equivalence will be made clear by introducing some other notation.
Are we supposed to understand your claim, or will you prove it?
I will prove it.
Okay.
Yeah. Yeah.
Is this are you saying this is a fractal model? Or
Yes.
Yes.
Type 2. For those who have heard about the checkerboard model, it is marginally different. In the checkerboard model, this term was absent. This factor was absent, but the z was just there. I just removed that single z to this. So I thought about the name for it, and the perfect name for this is did I spell correctly?
I don't know what you're trying to write.
By definition.
Oops. The flower that blooms metal. Oh. Yeah. Yeah. Right. Yeah. Sorry. Because it look like a you have something, and everything is just floats up there. Yes.
Since you mentioned checkerboard model, can
Yeah.
you motivate like why this change is interesting?
Would you wait for another 30 minutes?
Okay, sure.
Yeah. Yeah. Okay. So, I'm really speaking about the very simple class of models. In condensed matter physics, you will encounter various kinds of complicated. Hardly anything is solvable. But here I'm representing Hamiltonian models that are always solvable, and forms a so-called stabilizer code Hamiltonian. It's a small class, but we should not underestimate the pedagogical benefit from these models. And it can be reached, as you see here. A mundane-looking thing is equivalent to 8 copies. Who named 8? Why does it behave strangely that doesn't follow the topological construction before? So, yeah, you immediately encounter some calculation problem. You cannot test a model by spending tens of pages drawing cubes. That's too much time. So we need to do it better. And for that purpose, let me explain the polynomial method. It's a yes.
Sorry, can I interrupt? Frank, I think a better name would be the anglerfish model. This fish with the light coming out of its head.
Oh, okay, okay,
Anyways, just a suggestion.
okay. Thanks. Okay, yeah. Let's forget about the quantum stabilizer code for the moment, and just resort to the classical coding theory. I'm not getting into any difficult combinatorics here, because it's just a notation difference. So I'm trying to write down a cyclic shifts of the fixed bit string, and you wanna let your friends know about this matrix for some other reason, but you don't want to type this matrix every time you send a message to your friend. But I can resort to the fact that it is cyclic. Every bit is rotated back to the first position whenever I go to the next layer. So all I have to send is just this bit string and the fact that it is cyclic. Okay. And the classical coding theorists have developed one convenient method to represent this, which may look not very convenient in the first place, but it becomes convenient. The rule is that to introduce a coordinate axis, maybe I should draw it in a different color. These ticks are not one, just a position of your coordinate system. I will write down numbers. Then I could write down the first row as 0, 2, 4, 5, 6, 7. Okay. Well, classical coding theorists have replaced these commas into plus signs and then put a placeholder variable x. X is really a placeholder. So I have successfully encoded the first row into this polynomial with the coefficients being 1 whenever the bit is 1 and 0 if it's 0. One advantage is that if you multiply by x the whole polynomial, the exponents will increase by 1. And if you identify x to the power 8 is 1, then it's basically the size of your length of your bit string. If you impose this condition, then the next polynomial multiplied by the x will exactly represent this bit string. So in other words, the variable x, which was placeholder, but it also can be interpreted as a translation variable or translation operator. Pretty clear, right? And now I will do the same thing. If you remember the, I think it was second time, that David asked us that whether every stabilizer code can be interpreted as some homology. And well, the answer was yes. And the reason was that I could only remember the positions of x, either it's a sigma x or a sigma z. And for each of them, I associated one bit. And I encoded the commutation relation in some inner product between those vectors. So I'm going to do the same thing. So if I consider one-dimensional, say, the Ising model, then the traditional notation is this one. Well, notation is too redundant if we restrict it to the translation invariant stabilizer code Hamiltonians. Why? Translation invariance means that I don't have to remember the summation. Well, sigma is a waste of chalk. I and I plus, why should I have I? I only need the fact that this z is separated by this d by distance 1. That's all. So the 1 is important, but not the I. Tensor products is again a redundant, right? So I'm left with just this. And if I associate bit string for this one, say 0, 0, 1, and another one 0, 1 there, and then I do the same thing here. So I will write down two polynomials corresponding to the sigma x component and another for sigma z component. So sigma x component will be 0 because there's nothing. And sigma z component is that, according to that convention, it's just going to be this. Yeah, so any question about the notation?
Can you please repeat?
Oh, okay. So you saw my erasing. I erased the sigma, well, yeah, the summation part, I index. All I have to care about is the which type acts where and how much they are separated. That's all the information I need. So, and Pauli matrix can be encoded, one single Pauli matrix can be encoded in 2 bits, whether there exists a sigma x component or sigma z component. Sigma y is considered to be the product of the two, so I will just write down 1, 1. So I would have generally 2 components, one for sigma x part, the other for sigma z part. And I introduce the coordinate system where I labeled each qubit by some integer. And I raised that, and I wrote that coordinate system into the exponent of x, a placeholder. But it happened to have meaning of translation. So I end up with this notation.
So suppose you have 3 body interactions, and you would have a 1 plus x squared.
Exactly. Yeah. Okay. So as an exercise, let's represent the 1,1 toric code in that notation.
How will you represent the Ising model with a field in this notation?
Sorry.
If you have like zi plus zi times zi plus 1
Uh-huh.
plus like z on one side.
Yeah, that's well, you could write down such a term. Well, I could just extend this matrix by adding another column to represent the other type of interaction or other type of field term there. In that case, well, transverse field term will be just this. Longitudinal field term will be that. But it lacks any information about the coupling constant or field strength. But it didn't matter because we are always considering commuting terms. So you should not use this notation for non-commuting Hamiltonians. Although you can check the commutativity, as we will see, using this notation. So yeah, the promised exercise. Let's represent the toric code in that polynomial language. So here, the translation structure is very important. I should not arbitrarily change my translation because it's directly encoded in the placeholder variable x. So, which means I have to pick a Bravais basis vectors as well as the definite unit cell. And for the 1,1 toric code, there are 2 edges associated with the 1 Bravais lattice point. So my unit cell size is 2. So I should keep track of that. So this x lives on the vertical. So let me call that as EV, denoting the unit vector in the vertical unit cell. And this x lives on the horizontal. So it's going to be, it's just another placeholder. This x lives on vertical units, the qubit, but in the Bravais lattice point that is translated to the y direction, into -1 direction. So, and this one is same for that, but translated to the left in the x direction. So it's going to be and the same for the, well, so I only denoted the sigma x part. This is for just the bookkeeping of where I put the sigma x and bookkeeping of its position of the qubit in the unit cell. Well, what about the Plaquet term? Again, I think of the same unit cell. So the Plaquet term would be, there's no sigma x component, but there is these are just placeholder. Okay, and just look. Oh, because, well, if I pick an origin here, then this x is on the left. Yeah, but if I pick if I pick origin, say here, then this z is on the positive part. course, the choice of origin is my arbitrary. Okay.
So can we also write 1 plus x? Is that also legit
1 plus x where?
in the for the z?
Here?
Yes.
Well, you should be consistent. If you want to write this as 1 plus x, then you should write it as x plus x y inverse. Yeah.
Switch y in face in the second vector?
No, I did not look for this one. I just literally copied the position here. This is 0, 0. This is 1, 0. This is 0, 1. So this is y1. This is x1.
Yeah, so
Yeah.
why you put y on the horizontal and face on the vertical?
Because this was my EH, and this one is at, well, again, horizontal direction. So you just carefully look at the position, and this matrix is supposed to keep track of only that information. So for any translation invariant stabilizer code Hamiltonian, you can write down such a matrix, and each column would correspond to different type of interaction term. In the toric code case, there are only 2 types. In the 1, 2 toric code, there will be 4 types, because we are insisting on the strict translation invariance. So Placket term orienting this direction is different term than Placket term orienting that direction. And I subdivide, well, it comes with the 2 large blocks, and the row within that block labels the position of the qubit within a particular unit cell. Okay? And yeah, now we can express this one in that language as well, but let me give you an exercise to keep track of all the exponents carefully, but just write down the answer.
The bars mean inverse?
Yeah. I hope that I didn't make any mistake. Yeah. Yeah. They are, yeah, right. Oh, here the unit cell convention was somewhat different. Since I exploited the fact that I only work through the checkerboard lattice. So in the checkerboard lattice, the unit translation is not the usual coordinate translation, but translations along the phase diagonals. So this is my X translation. That's my convention. And that's, well, the face on the back, the face diagonal, that's my Y translation. Well, I left, it's left oriented, but it doesn't matter. And the face diagonal on the bottom square is my Z. Okay. So what does it bias?
So with a matrix like this, it's specifying just, you write one of these matrices. For each stabilizer, you write a matrix like this, or?
So each column corresponds to one type.
Okay.
So here I drew sigma Z type. So that will correspond to,
Zeros there.
0 means that, well, so one column means one type of operator. So the fact that it only occupies the bottom part, meaning it only consists of sigma z's, and the vice versa for sigma x. Yeah. And you can also do the same exercise for this model too. I recommend the translation vectors to be these.
So the structure that for each interaction you take like the inverse of.
No, no, no. That happens to be the case, but I do not insist on that.
Isn't it? Okay.
Yeah, yeah. That just happens to be the case. Okay, so having introduced new notation, now we can think without drawing figures. We just focus on the polynomial and try to interpret what it means. The less is better. It's better not to write down actual polynomials. That way you can focus on the structure more. So suppose I have written down such a polynomial matrix. Matrix is supposed to act somewhere, right? So if I plug in some column vector here, well, let's try first with the unit vector. What's the multiplication rule mean? The image will spit out certain column vector, and especially it will read off to say the first column. But the first column was just a notation for the single type of Hamiltonian term. Well, likewise, all the unit vectors will produce my Hamiltonian term. What if I had 1, 1 here? That will add these two vectors together on the image, right? But what does the plus mean? I replaced every tensor product into plus sign. And it made sense precisely because polymatrix is square root to 1, square root to identity. So whenever you see a 0 there, it means that you act by identity there in the Pauli representation sense. If you have 1, there is something. So plus here means that you multiply these Hamiltonian term with that. In terms of stabilizer coding language, that's another stabilizer. Any question on that? Yeah.
But if we assume we have two same rows, then it should be 1, right? Just identity operator.
Say it again.
If you have two same rows of stabilizers.
Same rows of stabilizers. Oh yeah, yeah.
Yeah, it should be 1. And then
Yep.
I don't see with these polynomials how to do it.
Well, in that case, you are doing this. You pick a same term here, and another, well, the same operator twice, and you are going to multiply them. So that arithmetic is faithfully represented in this notation. Okay. In other words, in this space that is going to be fed into this matrix will denote the collection of Hamiltonian term labels, and upon multiplying this matrix, it will tell you what the result of multiplication is.
So we don't multiply in normal sense.
Sorry?
We don't multiply in normal sense.
So I'm lifting the multiplication in the Pauli matrices into addition in this notation.
Can you make an example?
Okay, so let's do it here. So, well, here I should combine it to write it as And I suppose I multiply by 1, comma 1. What's the result? Right? But, yeah.
But if you have on this is easy, but if you have like like on the top string, not 0 but something.
Here?
All right.
Here?
Second column, if you have something on top.
Oh, here. Like, oh, yeah, like, I don't know, maybe something like this. Yeah? Then it will be this. That will just be the product of the Pauli operators represented by these two columns.
So we add modulo 2, right?
Add modulo 2.
Okay.
I don't understand the meaning of the vector limits applied to your matrix. Why one? Why? How do you choose 1, 1, 0, 1? What's the meaning of those one?
What's the meaning of this number?
What's the meaning of this vector?
Oh, so the first component will choose this stabilizer generator. Second component will choose the second generator. The fact that they are both present means that I will multiply them together. That's it.
Okay.
Yeah.
That's saying that's special.
No, no.
Okay.
Yeah. So this notation, although each column contained information about the actual Hamiltonian term in your system, in your definition of the code, but if you consider arbitrary input vector here, then the resulting is just the full stabilizer group. You know, the stabilizer is not specified by the specific generator. It's a group that makes perfect. Well, that's more meaningful. So it captures that by thinking of the matrix as a map. Okay. More important thing that I want to stress is the transpose of that matrix.
There is elementary Hamiltonian, which is defined by that matrix,
Yes.
which contains all the stabilizers.
Yes.
Kind of a basic Hamiltonian. What is the relation between Hamiltonians that you generate by taking different vector, multiplying that matrix by different vectors? Like what's common to them?
Great question. Their ground space is the same.
They're what?
Their ground state, subspace are exactly the same. You know, remember, so if I give you a Hamiltonian that looks like some stabilizers like this, then by definition the ground space is the common eigen space of eigenvalue plus 1.
Oh, I see.
So immediately if I look at, as soon as I look at the ground space, it forgets about the fact that it was coming from this, but only cares about the group structure. And I wish to encode only that information.
I see. That's why you.
Yeah.
Just a question on notation. In this case, shouldn't there be 6 rows for the different
In which case?
in the dandelion model?
No, actually 2.
Last check.
You should not rotate it. The orientation is fixed. Yeah, the stem is pointing always along that body diagonal direction.
Okay, so are you just not writing one of the lattice vectors in that? Or maybe I'm not understanding. I thought the rows are labeled by X and Z.
Yes.
And also this direction or the edge along the.
Oh, you mean this part?
Yes, yes.
Yeah, I just didn't write it.
Okay.
Yeah, I just didn't write it.
Okay, the question is 3D, shouldn't there be 3?
No. The number of rows is unicell size. And in my choice of the Bravais lattice along the face diagonal, the unicell size is 2.
How do you choose a unicell?
It's my choice. Yeah.
In this picture, what is the unit cell?
Oh, in this picture, I chose unit cell to be this one, the body diagonals. Yeah, I was supposed to talk about, I was going to talk about the transpose of this map. Why? Because we're interested in the excitations. So starting with the ground state, apply certain Pauli operator. How do you figure out where the excitations are? You just look for the commutation relation with Hamiltonian terms with the given Pauli operator. That's it. Right? So then, well, let's forget as much as we can. What's important? The phase vector in that Pauli operator doesn't matter at all. The location of Pauli operator obviously matters. And whether there are sigma x or z type obviously matters. Right? And we can revert the commutation relation from this bit representation. Do you remember this equation? If I represent x as 1, 0, z as 0, 1, then this minus 1 is exactly the inner product where you take the inner product after interchanging the two components. That was the rule. And that encodes everything about this phase vector from the commutation relation. So if you represent the Pauli operator that is acting on the ground space by these polynomials, then there's a chance that you can recover the locations of excitation by reading this matrix. It's a simple mental exercise, so let me not go through the actual derivation, but just state it. The rule is that it's given by this. So take a transpose, make every variable to its inverse, and multiply this z and x interchanging matrix. And then to read off the excitation, you write down your Pauli operator that you will act on the ground space as a polynomial in the column vector using the same rule. Do the matrix multiplication modulo 2, including the polynomial vectors. It will give out some certain vector. And then it should consist of like 1x, some y, I don't know, xy, and something. And it means that, the first term in the Hamiltonian is flipped at the origin and an x 1, 0 and at 0, 1. And second type of Hamiltonian term is flipped at 1, 1, and so on.
So the matrix you wrote should be self-orthogonal with respect to the different lines.
Exactly. So now, what about the, I briefly mentioned this, what about the condition that the Hamiltonian terms themselves do not generate excitation? Hamiltonian terms are again some Pauli operator. So upon acting on the ground space, it does something. We want to figure out what that is, what it does. But we constructed the ground space such that it does nothing, acting by identity. And that translates to the fact that if I plug in any column from the sigma matrix, the result must be 0. So the condition that your Hamiltonian commutes becomes this matrix equation over the polynomials. So now you see some of the usefulness of this notation. If you were to test whether your Hamiltonian is really commuting between x and z term, how would you do it? You would write down or draw each term and then bring another term of x type, and then whether they are meeting at even locations or not. Can be painful, can be error prone, but here it becomes just mechanical calculation. The only pain you should pay is at the initial stage to translate everything into the polynomial. That's it. The same thing be useful here too. You should test your commutativity across all cubes that could touch the Hamiltonian term. But once you have translated to the polynomial, the commutativity test becomes just a mundane polynomial multiplications. Oh.
I'm really more convenient. I don't get the feeling why I would use this addition instead of just drawing two cells and looking at them and say, okay, it's obvious they overlap at four sides and they commute or not.
Yeah.
I don't think I would get why I should use this one.
Complexity theoretically speaking, it only saves you a constant. Yeah, they are equally efficient. There is no doubt about that. But somehow I found it is mentally more simplifying. And one more advantage. This way, you can think of now a family of Hamiltonians, not just a particular model. All you have to satisfy is that equation, the matrix equation. Any solution to that will give you some code, trivial or not, that I don't know. But now you can talk about any arbitrary family. Yeah.
So what happens if you have, say, excitations in two different unit cells? You can also read in that map. So
Yes. Excitation in different unit cell. Well, excitations are associated with Hamiltonian terms, not necessarily with the unit cell structure.
No, I mean, here everything is written for one unit cell. Like interactions acting somehow in one batch. System, right?
You're imagining the term
So
should...
here we wrote a plaquette term.
Yes.
And a vertex.
Yes.
So now thinking like if you have excitations in two different vertices or in two different plaquettes,
Two different...
you
Yeah.
can also read it here.
Yeah.
Directly from the result.
Yeah. Because they're all related by translation, and the translation in this notation is multiplication by monomial.
Okay.
So, okay. Now let's put the error correcting criteria in this language, and I think I should almost stop there. So, we got two matrices. One that describes excitation given insertion of some Pauli operator onto the ground state. We have another map that tells us, given a set of generators of the stabilizer group, I can read off the actual stabilizer group element laying out on the lattice. And the fact that if I compose the two, results in 0, reflects the fact that my Hamiltonian terms were commuting with each other. Yeah.
Is there a mapping from those two operators to the generator matrix and adding like the Paris check matrix?
Pauli?
Is there like a link between those two operators and like the generator matrix and the Paris check matrix?
Oh, yeah. Oh, good point. This is a compactified version of the parity check matrix exploiting the translation structure. So if you write down, if you associate a certain basis vector for each lattice point, and then represent all possible exponents to be in the different unit vector, then you can just write down a gigantic matrix out of this polynomial matrix. Matrix size will be proportional to the system size volume. Yeah, it's a simplified notation for that, in that regard. Now, let's distinguish between local operator versus something non-local. If you remember the Topological example or any other example in the topological system, the operator that acts on the system has a property that it wraps around the system. If you think of a growing system sizes, that operator support should grow as well. Translating into this framework, it means that your polynomial vector must contain ever-increasing number of terms in it. Put differently, if you give me any polynomial is by definition consists of finitely many terms, and you consider that a size of, well, that operator to be much smaller than the full system size. So having a polynomial of bounded degree means that you have a some finite operator on a bounded region, right? So if I have a certain operator that results in no excitation, say, then to make a topologically ordered, we want them to be trivial. You remember the Knay-Laflamme condition? This condition. So OA was any operator that is of bounded support, acting on the ground state subspace results in the scalar multiplication. When this is unitary, it's either when it's a poly operator, then it's either 0 or 1. Right? So any finite operator resulting in no excitation, we want them to be trivial, but those trivial operators should always come from the product of Hamiltonian terms. But that's precisely what this map describes. So working on the infinite plane, the kernel of this map, something that maps to 0, must come from product of stabilized generators, and that is this.
They're just the same in trivial homology group.
Exactly. So if you now this is the reason, very reason I spend significant time explaining homology. We attach the homology groups to explain topological invariant, and the way we constructed homology groups were closely tied to the triangulation structure. But the algebra, after you have constructed triangulation, the algebra is just an algebra. Computing kernel, taking the image, has nothing to do with the topological space, although it came from it. Now we're exploiting that algebraic fact. We have a certain chain complex consisting of 2 maps, well, at least 2 maps, and then whose composition is 0. And we interpreted that the vanishing homology, well, this is equivalent to this is 0. The vanishing homology condition into the condition that our Hamiltonian must be a good error-correcting code. And this point of view allows us to leave from the usual topological construction of models. Why should sigma carry topological interpretation? Perhaps not, and indeed not. Did I erase? Oh yeah, I erased it. Yeah, as long as this homology group vanishes, and if you could cook up some sigma matrix in such a way that this homology vanishes in some dimension, then you automatically get some good code, which we have been calling topologically ordered. So that's the departure from the traditional perspective. And the Dandelion model was one example of that. If you solve any generic equation of the commutation relation, then typically you end up with this condition satisfied. So in that sense, topological order systems are very easy to find in this framework, at least.
I'm a little confused because before, sort of the size of the homology group was related to the number of logical operators?
Yes. In this case, it will be same, but the important point is that here, this is infinite plane. This is infinite space. Any polynomial,
It's the bulk.
yeah, it's a bulk. Any polynomial that has a bounded degree is interpreted as a local operator acting on the bulk. And if you put some periodic boundary condition or some non-trivial periodic, some boundary condition to make your space to be topologically non-trivial, then you should compute the homology with respect to that boundary condition.
Oh, and then it will not be 0.
Right.
Oh, I see.
Yeah.
Or you can include like Laurent polynomials, right?
Yeah, everything is Laurent polynomial. Yeah. So inclusion of the boundary effect affects this homology, and that will carry over to the number of the ground space degeneracy, and so on. And let me use like 5 more minutes or so. So another promised proof that my Dandelion model did not have any string operator. How does that translate to this? So now we invoke the definition of the string here. Okay. So the first condition says a string operator should make an excitation at 2 different locations. So I should be able to, well, some string mapped by this map should result in some polynomial, but I could group the terms in that polynomial with respect to their distance into 2 blobs. So I could have like 1 plus x, y, xy, something, and plus 100 some translation of something else. Right? And the second condition means that I could increase this exponents. Well, yeah, there exists a sequence of string operators such that it results in increasing these exponents in absolute value. Okay. And for the polynomials I draw, this excitation map restricted to the sigma x type up to unicell up to origin choice is equivalent to this. And you can show that any combination of these 2 polynomials cannot generate such a thing unless each of them has their own pre-image. So each of them has their own pre-image means that, forget about that term. This term comes from something here, but something has to be some bounded operator, so local operator. So in other words, this thing is a locally created excitation, has no topological charge in it. So it becomes a purely algebraic problem. You don't have to work with the diagrams anymore. Just examine the image possible combinations of these 2 polynomials and try to separate them. So, and you can, from this point, you can make use of some elementary facts about algebraic geometry. You solve that equation, find the 0 locus. That's the powerful method to examine the possible combinations of these polynomials. And then interpret that solution in terms of these exponents growing. And that gives you a mathematically rigorous proof that this model lacks any string operator. So you see now you okay, so maybe you have seen too many mappings. So let's recap before we say bye. Yeah. Any question? Yes.
So what are the logical properties?
Good question. I plan to do, but obviously I ran out of time. So what you have to do is, well, let me give you an example. So epsilon is this matrix. Consider this. Consider this input to my excitation map. Then the result is it becomes power of 2. So if you are if you put the boundary condition the periodic boundary condition of a power of 2 size, say, then since you are working over the modulo 2 arithmetic, powering of a power of 2, you don't have to worry about the cross terms. They always have an even coefficient in front, so they always cancel. And this result is this. And if you put the periodic boundary condition so that where you identify these translations to no translation, then everything becomes 4, and 4 is 0 in mod 2. So it becomes no excitation situation, and the operator you have inserted there is a logical operator. And you can figure out by expanding this exponent in a self-similar way to realize that, oh, it has a fractal structure in it.
Why is excitation like size 2 should be size 4?
I'm just presenting one particular example of logical operator. Yeah, there are many. There are many other. So let's, yeah.
So here you wanted to allow all possible operators which can create 3 or more excitations, right? So
3 or, yeah, right. 3 or more is allowed.
so you put that condition in by, so in that, so what is contained in E that shows you that there are 3 excitations, for example?
Well, there is no such thing in this particular example, but you can argue yourself why that has to be the case. Yeah, but I wish to end the talk without talking about that particular example, but somewhat speculative remarks. So what we have done, we focused on the stabilizer code Hamiltonian only. I have not talked about anything else. But the main reason for that is we can still learn a lot from that class. And it has an easy interpretation in terms of error-correcting codes. And then I remarked on the homology and the usual construction. Right? And the homology in that case comes from the actual triangulation of some manifold. But homology itself doesn't have to be related to the topology. It can be purely algebraic, and this is one way of relating such. Although I don't know anything else, that's up to you to extend. So from this point of view, we have constructed some exotic thing that goes beyond the traditional framework. And the so-called fractance arises almost always if you follow this. The toric codes are so special examples in this approach. If people have developed the coding, well, if people started to write the Hamiltonians using this, toric code might have come much later. Still, the quantum memory problem is open, although I did not discuss anything about the dynamics of this particular example, but the energy barrier is not as good as we wished. In the 4D toric code or two-dimensional classicalizing model, the energy barrier was linear in the system size. Here, it's only logarithmic. And logarithmic energy barrier is not strong enough to suppress all the entropy contributions. And this functions as a quantum memory that not as good as I expected. So the question of self-correcting against the thermal errors, quantum memory is still open. Understanding why either direction will teach us a lot, I believe. And this approach puts a big question on what do we mean by phase of matter? Why do we have to put the word topology in front? Anything So this comes from the error correcting code, and the rigorous proof on the gap stability applies equally well here. So it is stable against arbitrary perturbation. The gap splitting is exponentially small in the system size. Everything carries over, except the intuition about the relation to the topology. And I didn't discuss about it, but the ground space is fluctuating a lot depending on the system size. It's a crazy function, some number theoretic function. Then you can ask the usual definition. You should revisit the usual definition of phase of matter. The usual definition is such that, well, two Hamiltonians are said to be equivalent whenever they can be interpolated by an adiabatic path that doesn't close the gap. Great. But we cannot always speak of infinite systems to make something more sensible. Then we are bound to the sequence of finite systems. But if the ground space itself has a distinct dimension according to the system sizes, how should I connect the adiabatic path? This is called cubical model. Is the cubical model should be equivalent to itself, but the system size choice or the unit set size choice is up to my arbitrariness. Where should I put the adiabatic path into? Should we think of some subsequence of it? Maybe. That poses a fundamental question on the mathematics of a phase of matter. And although this framework allows us to find many new models and analyze some hard calculations into purely algebraic calculation, it does not say too much about how to distinguish them. Well, equivalence is always easier to show. You just find equivalence under a suitable, reasonable rule. Showing they are different is a totally different matter. And that's, for that question, is largely open. Yeah. For instance, I chose a different unit cell to make the Hamiltonian look different for the given two polynomials here. One is the usual thing that you may have seen in the simple cubic lattice with the 2 qubits per site. Here, the Dandelion model had a different unit cell structure, but it turned out to have exactly the same algebraic structure. Are they really different in the usual sense? That's still unanswered. Maybe we should allow more equivalences to make any progress. That's another speculative remark. And I have not talked at all about the duality mapping in these cases, and that's also an interesting topic to consider. I'm one of the authors on a paper that discusses the gauging procedure for these fraction phases. But now I admit that for type 2 phases, I'm not completely sure what we are gauging. The reason is, usual gauging procedure, you plug in degrees of freedom corresponding to the number of gauge the global symmetry operator, right? But for fractal phases, if you think of the dual version, the number of symmetry generators is not just one. They're more complicated. Although in the duality mapping, we're inserting only 1 qubit more. So what we are gauging. There's no problem with the duality mapping. It's just duality mapping itself is a correspondence between 2 different Hilbert spaces using some non-local unitary. So that part is okay. But to interpret it as a gauging, we need something else. Okay, with that, I should conclude and let's have lunch. Thanks.